Guys, let's take a look linear motion equation first, and then we'll discuss the projectile motion afterward. Okay. Linear motion, we talk about x-axis and y-axis motion separately. So usually we can consider any object moving on x direction, horizontal, y direction, vertical, and then any vectors upward direction should come with the positive sign, any vectors downward come with the negative sign, any vectors horizontal right positive, any vectors horizontal left negative sign. Okay, so we developed three important equation by assuming acceleration is constant, right? If acceleration remains constant, then we know by definition the velocity is equal delta x over delta t, and average velocity also we can define the initial plus the final divide by 2, and the acceleration we can define delta v over delta t, which means v final minus v initial divide by the time. By combining these equations, we develop these three equations, right? V final is equal v initial plus acceleration times the time, and delta x or y is equal v initial t plus v initial t plus acceleration over 2 t to the power 2, and v final square is equal v initial square plus 2 acceleration times the delta x. Now these three equations are we generally call the linear equation, and the equation can be used whenever acceleration is constant, either x-axis or y-axis or any other direction, but only straight line motion. Okay, when we're talking about y-axis motion, we were interested only y direction, we interested only motion under gravity, we generally call the free fall motion. So if I have an object which is free falling, then we know the acceleration along y direction becomes the gravity. Gravity is always equal 9.81 meter per square second. As a result of that, all these three equations I can rewrite. V final along y is equal V initial plus gt, and delta y is equal V initial yt plus g over 2 t to the power 2, v final y square is equal v initial y square plus 2g delta y. Okay, now the idea of the chapter number 4 is actually using these equations simultaneously when object moving in between these axes. Okay, so that we generally call the projectile motion. So let's take a look. So the before we go into there, let me summarize very quickly what happening if the acceleration is not constant too. You need to take a look the last lesson video on that. So not constant. If it is starting to as a function of time, now the acceleration time. As a result of that, I cannot use previous equation. I have to use the integrals, right? Which means acceleration now function of a time, acceleration going to be equal dv over dt. I cannot use the delta. I can use only instantaneous scenario because now acceleration continuously changes. It's not remaining constant. Okay, so in this situation I can do dv is equal a times dt. Then if I integral this one, then my formula becomes slightly different. V final minus v initial is equal integral a dt. So this is time goes from 0 to 2, 0 to t. Now to do this integral, I need to have the function for the acceleration, right? Then if I know the velocity function from here, you can see I can figure out the velocity final equation, which is equal v initial plus integral 0 to t a of dt. Then if I know the velocity function, then I can use the velocity definition in terms of instantaneous, which is dx or dy over dt. Then from here I can find the displacement function, which is integral dx integral v dt. This goes from x initial to x final. This goes from time 0 to t. Then this going to be x final is equal x initial plus integral 0 to t v dt. Okay, as you advance slowly into your calculus classes, particularly the calculus 1, maybe second half, then you learn all of these integrals, then you should be able to do situation whenever the acceleration is not constant. Okay. All right, now let's take a look the idea of the projectile motion. In terms of projectile motion, object start moving on a parabolic path, so which means we're gonna send the object initially somewhere in between the x and y axis system. So the object gonna be start from here. We will project it theta degree angle relative to x-axis with some initial velocity. Then what will happen to this object? This object will starting to move upward, but the gravity is always dragging it downward. As a result of that, initial to velocity component, you can take a look x direction. I have v0 of cosine theta. Y direction we have v0 of sine theta. Then this v0 of cosine theta remaining constant. The reason whenever object is in the air, x direction there's no acceleration. A x component will be 0. But the y direction always gravity dragging downward. This object is starting to slow down along y axis. So it's slowing down slowly along y-axis. We'll reach some maximum height right here. We'll start going downward direction. So if you look at the path, that path is very parabolic. So that's why we call this parabolic motion. Okay. This called the maximum height. So we can say delta y is starting from A to B and then B to C, it's coming back to the ground. Gravity is always downward. Upward velocity slow increases and then eventually reach here. Upward velocity Vy component is 0 at that particular point, point B. And then it turn around and then slowly increasing downward, eventually right here, gonna reach exactly the starting velocity. Okay. So that's the idea of the projectile motion. Now, the what's important here, I can't really use my equation randomly in any direction. My equation can be used only a straight line. So which means I can study the projectile by observing this motion along x-axis and along y-axis simultaneously because there's one parameter same for both direction. That is the time. Okay, time parameter same for both direction because the both direction motion happening at the same time. If you consider A to B motion, during that A to B motion, object goes up about delta y, object go horizontally about this A to D distance, right? So it go upward ay delta y amount, it go horizontally A to D amount. These two happening during the same time period, time of AB. Since the time remaining constant, I can connect the two motions together by using the time values, and then I can apply the linear equation simultaneously on x-axis and y-axis. Okay. Now, if I want to study this, let's take a look the x direction motion first. If I look at the x direction, then we know x direction whenever the object is in the air, acceleration along x direction becomes 0. As a result of that, if I apply linear equation along x direction, I gonna end up only this formula. Delta x is equal v0 x direction times the time. So V0 x is V0 times the cosine theta times the time. X direction, I have only this equation to work with. I'm not going to have any other equation during the motion along x-axis if the projectile is moving just on there, okay, without any other influence. However, if you look at the y-axis direction, on the other hand, y direction acceleration becomes gravity. A of y is equal g. G is always negative 9.81 meter per second squared. Y-axis direction, I can apply all of these formulas, okay, because acceleration is there. So I can rewrite all of these equations. V0 yt plus g over 2 t to the power 2. V final y square is equal V initial y square plus 2g delta y. So the y direction, I can do exactly same thing which we did on last chapter, but the x-axis now I have only one equation to work with. This amount the displacement along x-axis A to C is generally called the range of motion. Okay, so to do the range, I have only one formula, but to do the y-axis study, I have all of these three formulas. Okay, and in terms of range, we can rewrite this formula by finding the time of motion. We will do that in our next slide. All right, so let's take a look now. If you go into the detail work of the projectile, there's a we can categorize all different type of projectile into like 4 different categories, which mean like you you send a soccer ball or basketball into the basket or football into another place in the field, and then so on. We can generally categorize these motion into like 4 different type of projectiles. Okay, that's what we're going to study in this chapter. So we will take a look each type very briefly, and then we will do question during the class time. Now this is our type 1 projectile. This type 1 projectile, you can see I have football starting here. Let's consider starting with initial velocity v0. Angle is theta. So this is x-axis, this is y-axis, this is the ground level. So now projectile is actually sending from the ground level, okay, starting from ground level. So we know x direction, I have v0 of cosine theta velocity component, y direction we have v0 of sine theta velocity component. Object will eventually reach this point right here, we call the maximum point. At that maximum point, our velocity component momentarily becomes zero. Horizontal velocity component remaining v0 cosine theta, because that direction there's no acceleration. Okay, and then let's consider this is point A, point B, point C. When you reach point C, y direction velocity component is actually become same as the starting point vc of y. Vc of x is still going to remain in the same as v0 cosine theta. There's no acceleration along x. Y direction acceleration is the gravity. Gravity is always pulling this downward direction. Okay, now if you look, this is a nice parabolic shape. A to B motion is symmetric to B to C motion. If I can find, for example, time from A to B, that time should be equal to B to C. So the total time from A to C, for example, I can figure out by finding the time from A to B and then multiply by 2 times. So that we call the total time. And the total displacement, x-axis direction delta x, is the range, which is the amount displaced from A to C, okay? Range of motion. And then height from the ground level to B, we generally call the maximum height object can reach, which is the delta y. Now, all of these information we can simply figure out by knowing just 1 or 2 parameters. Let's say, for example, if V0 given, theta is given, then by knowing those two, we can figure out all of these. We can figure out the time, we can figure out the displacement, maximum height, all of those things, okay? That what we're going to do during the class time. So in this case, we will take a look very briefly how to figure out, for example, the total time, assuming V0 and theta is given. Okay, we'll assume V0 is known, theta is known. Then I need to find the total time. So let's consider y-axis motion. We'll apply delta, we'll apply V0, V final, y direction is equal V initial, y direction plus acceleration towards y-axis times time. This is, I'm considering A to B motion, okay? If I consider A to be motion, then the time from A to B, which is equal V final minus V initial divided by the gravity. V final going to be 0. This is minus V initial over gravity. So the minus V initial is V0 sine theta divided by G. Okay, that is the time from A to B. Now total time from A to C is twice this number, because this is a symmetric motion. Okay, not every projectile symmetric. You need to take a look that very carefully. Now, since I know this time, this is the total time now, right? So since I know the total time of the motion, by using that, I can find every other thing. For example, let's say I want to find the range. Then the x-axis direction, we know we can use only one formula, v0x times the cosine theta. V0 times the cosine theta times the time from A to C, total time. If you put the time here, then I will get V0 cosine theta negative 2V0 sine theta divided by the gravity. And if I multiply this together, then I will end up negative 2V0 square cosine theta sine theta divided by G. That's the delta X, okay? Now this formula, that negative sign going to cancel out because G is a negative number. Now this formula we usually write this way. So we usually write this negative V0 square over 2 V0 square over G multiplied by the sine 2 theta. Why we write in that way? The reason is the trig identity. If you take a look carefully this part right here, I can have a 2 cosine theta times the sine theta. That is actually equal sine 2 theta. That's it. Now this we can use, this idea right here, delta x range, we can use to prove the maximum range. If you remember last experiment, we actually try to understand the maximum range by projecting the object with various angles. Then, if you remember that, then if I draw a graph, theta versus the range for various different angles, my data set was look like this. Okay. Then if you draw a line between them, that line becomes a parabolic shape, then I should be able to find the maximum point, maximum we can say theta for maximum delta x, and then this gonna be the maximum delta x. We can say the range max. Okay. Now, when the range becomes maximum, we know in generally theta should be something close to 45 degrees. Let's take a look how that happens. So how that happens, now we know range formula we can write, which is the delta x is equal negative V0 square over G. That negative sign going to cancel out because the G is a negative number, okay? Negative 9.81 meter per second squared, and then multiply by the sine 2 theta. Now, if we keep the initial velocity constant and the G constant, V0 and the G remaining constant, then we know range, which is the delta x, which is a function of sine theta, right? It's going to be proportional to sine theta. So sine 2 theta. So the sine 2 theta can varies only between 0 and 90 degrees because the angle cannot varies in between that. The sine angle, any angle, let's consider theta. Theta can varies only between and 90 degrees, right? If I take the sine 2 theta, what happening between that minimum and the maximum angle, when the sine 0, then the value is 0. Sine 90 can happen only when the theta is 45 degrees, right? Because the equation has sine 2 theta. When the theta is 45, sine 2 theta becomes 90. Sine 90 is actually equal to 1, okay? Sine 90 is equal to 1. That's why this equation, the range maximum can happen only when theta is equal 45 degrees, okay? However, you have to be careful. Now, this range equation we're writing, this is a one type of projectile, right? This projectile, we started at ground level. That you need to take a look carefully. When the projectile is started at ground level, then this equation is actually valid. However, there are various type of projectile. We'll take a look. This equation can differ into a different type if the projectile is starting initially at different location. Okay. So let's take a look couple of other type of projectiles. So this is generally called type 2 projectile, also called the horizontal projectile. That's our part 1 of the last lab. Horizontal projectile means initially we're launching this object somewhat height h above the ground level, but initial velocity component we keeping only on x direction. Okay. So this is going to be vi of x. We can say initial velocity v0. And if I do that, then let's consider this is A, this is B, this is C. A to B motion downward happening same time as the B to C motion horizontal. So this is going to be the delta X amount in moving horizontally. Time from A to B vertically should be same as time from A to C total time in here, because this is the half the projectile, or time from B to C horizontally. Now again, if let's consider if I know V0, then I can find all the other parameters, right? So if I know V0, then we know gravity also we know. Then I can consider y-axis direction. I can apply delta y is equal V0 VIY initial y t plus g over 2 t to the power 2. When object project horizontally this way, initial downward velocity component, the initial y is 0, then this whole part becomes 0. Delta y is h, which is a negative number. Okay, so the negative h, which is equal, gravity is a negative number. So this is going to be just g over 2 t to the power 2. Then the t becomes h 2h divided by gravity square root of that. Okay. Now that is the time from A to B vertically. Same during the same time, object goes from B to C. This is equal to B to C. Remember, h is also a negative number. Gravity is also a negative number because object go downward due to gravity, that negative direction. We assuming this is our starting point. Okay, that is our y0 point. All right. So which means if I plug this into x-axis direction, in x-axis direction, we have only one formula to work with. Delta x is equal v initial x times the time total. The initial x remaining the same, delta x is equal v0, time is 2h over g square root of everything. Now if I know v0, h and g, so I should be able to find the range. Now you can see this range is not the same range equation you had earlier. That's what I mean earlier. Okay, now this formula is very different than this range equation. Okay, this is completely two different projectile. As a result of that, this equation you have to carefully analyze before we do anything. Okay, just generally can't use any equation as a general equation during different projectiles. You have to carefully check what is the type of projectile we are dealing with. Okay, this is another type of projectile. We can say type C. So this is the projectile which we initially sending a little bit above the ground, like we punting a football. This is x-axis, this is y-axis. Object will eventually reach that maximum height right here. We can say delta y. And initial y component of velocity v0 of sine theta. This is the v0 component. Initial horizontal velocity v0 of cosine theta. And v0 cosine theta remaining same because a of x is 0. A of y is always gravity. Gravity is always dragging downward, which is a negative number. Let's consider this is point A, this is point B. At point B, upward velocity momentarily becomes 0, horizontal velocity remaining as the initial velocity. As a result of that, it continuously moves. This is the level it reaching relative to the initial level, but it can't stay there because it has to go all the way to the ground. There's another small part here. As a result of this small part here, this projectile, not the type of projectile we discussed earlier. This is a different projectile, okay? First projectile was sending from the ground, now it's little bit above the ground. So everything is slightly changes now. If you look at it carefully now, in this particular case, for example, if I want to find the total time, I cannot do this way. Now the time, let's consider if I want to find the total time, T of total, that T of total, which is the time from A to D. Time from A to D is not twice time from A to B, okay? Time from A to D can be right this way if I want to, time from A to B plus time from B to D. These two are not the same now. It is not symmetric because of this extra part. You have to be careful. So I can find the time by using this way, or I can find the total time by considering A to D motion straightly on y direction. Okay, if I consider y-axis directly, then I can apply um, delta y is equal v initial yt plus g over 2 t to the power 2. Then that way I should be able to find the total time directly. In this particular case, delta y going to be h downward direction, which is a negative number, and the initial velocity component upward v0 sine theta times the time total plus gravity divided by 2 t to the power 2. Now this is going to become the quadratic equation. You need to solve the quadratic solution. This is going to be negative 4.9 times the t to the power 2, and I have positive v0 sine theta times the t, and then I have positive h number equals 0. H is the height. Okay, since I apply the negative sign here, I just need the number for h there. This gonna be A, this part is B, this part is C. If I know A, B, C, time I can find negative B plus or minus B square minus 4AC is square root of that divided by 2A. So the time must be always a positive number. Assuming time is always a positive number, you should be able to find the total time from here. Okay, so that's the idea. By knowing total time, I can find the range, other information. And the final velocity component here also, v of y direction d. This component is now completely different than this one. Okay, that initial y component is no longer same at point D, because now that is not on the same level horizontally. It's a different level. And then this going to be then completely different type of projectile. So that's where you have to be careful. Okay. And then let's take a look our last type of projectile. So this is type 4 projectile. In this case, like shooting the object to the basketball. Now, if I want to do this kind of projectile, it's still the same formula applies, but we have to work it out slightly differently. Let's consider initially start at height h. So usually the human, when we throwing a object to the basket, usually in the basketball level, we can consider initial height is about roughly like about like 7 feet or so. When you take a tall guy and then the hands goes up about like roughly about 7 feet, which is something like close to 2 meters. And the basket is usually about like 10 feet height. Okay, we'll do a detailed correction by using the real numbers. So this is going to be large edge relative to the starting point. Okay, and then for example, let's say I know how fast I throw the object. This is angle theta. If I know these two, then it will reach some maximum height right here. This is point A and this is point B. At maximum forward velocity momentarily becomes 0, but horizontal v0 cosine theta component remaining the same. Okay, and the forward velocity component is the only one changes as the object goes on this projectile path. This is a B, this is the C. Now you can clearly see this is not a symmetric projectile because this part is completely different, B to C motion. As a result of that, if I want to do the time, total time of the projectile, I can't say A to B time is equal B to C. That's totally different. Okay, so that is, I can find time for A to B, but that is not the same as B to C. However, again, if I want to find the time, there's another way to do this. Let's consider I know this h amount, I know initial velocity component, then we can easily apply again y-axis direction, because gravity is always there, dragging downward, acceleration x direction 0, acceleration y direction, gravity which is minus 9.81 meter per second squared always. Y-axis direction, let's apply delta y is equal v initial yt plus a divided by 2 t to the power 2. Then the y direction object goes up from A to C. We are considering A to C motion. That's going to be positive h amount, which is equal initial velocity upward direction v0 of sine theta times the t plus gravity divided by 2t to the power 2. So h is equal v0 sine theta t negative 4.9 t to the power 2. Then again I have a quadratic solution, negative 4.9 t square minus plus v0 sine theta t minus large h equals 0. Now this is your A, this part is B, this part is C. By knowing A, B, C, I can find the time, straightforward time from A to C directly, okay? Which is equal negative b plus or minus b square minus 4ac square root divided by 2a. Now, this is important, this time solution, okay? Earlier, time will be always become positive, but this case, if you solve this solution for the time, actually you will get two positive time values, okay? You might end up TAC two different positive time values. Two positive time values, both are correct. Both are correct. The reason, if you look at it through this line, this is the line, this is the level where the basket is. Through that line, projectile path is divided into two dividing a cut at two different locations, right? This is the projectile path here, it cutting here, and also this is the projectile path here, it cut here. So there's two different locations, point C and point D projectile path cuts. As a result of that, you will get two positive time. One positive time is actually whenever it goes to A to D, which is a smaller value. The second positive time is the time from A to C. So those are the things you have to be carefully, you need to carefully analyze. Okay, sometime we might end up just one positive answer, like in the previous case, we gonna end up one positive answer, then we find, because it's not cutting two places. It A to D, you can have only one time value. But here, you clearly can see you should have two time values, A to D motion and A to C motion. So we will end up two different positive time values. Okay, we will do real problems with the real life numbers during the class time. All right, that's it for the projectile motion. This is part A of this chapter. So I will put a different video for part B. Okay. All right, then I'm going to stop from here.